In today's lesson, we are going to be looking at the line of best fit. So we did mention this in the previous lesson when we were analyzing and organizing our data. We are going to look at it a little bit more thoroughly, and we're going to look at how to create one. So we're going to look at making one, coming up with it by hand, and we're also going to look at coming up with a more accurate one using Desmos or technology. So when we create a line of best fit, there is something that kind of gets attached to it, and that would be a correlation coefficient. So this is a number that we usually indicate or identify with by R that is used to represent how far the points are on average from the line of best fit. The closer the value is to +1 or -1, the closer the fit. So basically the more accurately we could say that there is a relationship between these two values. Now it is kind of on a spectrum or a continuum. So we have going from -1 all the way to +1. And the reason we have the negative and the positive is because of the type of correlation. It could be negative where we're decreasing as one increases, or it could be a positive where they're both increasing or where they're both, as one increases, the other increases as well. And then in between, it's kind of broken up into thirds. So anywhere between 0 and 0.33, whether it's positive or negative, would be considered weak. From 0.33 to 0.67, again, positive or negative, we would consider it moderate. And if it's from 0.67 upwards to 1, we would say it's strong. Now, if it's at 0, then there is no correlation. Right, so if it's 0, we would say that there is no correlation, or there's no relationship. So, for example, we're just going to sketch what we might think the general appearance would be of a scatter plot associated with the correlation coefficient. We're going to include a line of best fit where applicable, but right now we're just going to look at trying to draw the points or what the scatter plot might look like. Right, the line of best fit we could draw through. So if we have a rough axis, so an R value of 1 means a perfect fit in the positive direction. So that means that as one increases, the other increases. So this, I would argue, is a perfect correlation. We can see that the points are making a perfectly straight line. If we wanted to draw a line of best fit, they would go through all of them. So that would be an example of a perfect correlation. R is equal to -0.92. So this is almost perfect, but it's going in the negatives. So almost perfect means that as one increases, we're decreasing. So that might be something like this, where the points don't form an exact straight line. However, if I'm going to do my line of best fit, they're very, very close to that line. They're very close to following that trend. So there's a very strong relationship, or a very, very strong fit between the points and our line. If we had something that was 0.45 or a correlation coefficient of 0.45, this changes a little bit because now we're not as strong. We don't have a strong relationship here. We have a moderate relationship, so that means we should kind of see a pattern. We should see a little bit of a trend, but it's not going to be as tight and compact as what we've seen before. So this would be my example of a moderate correlation. If I wanted to draw my line of best fit in, again, it might be a little bit hard, but I would say there looks like a good line of best fit. Maybe let's draw a few more points below, just so we get a little bit of a separation. We see that the points seem to be kind of trending downwards a little bit. but our trend seems to say that it should be going up. So again, it's a moderate relationship. They're not as tightly packed together. Another way you could look at what type of or what the value of the R or the R value is draw a line or draw a circle around your points. The more box-like or the more square-like or rectangular-like your line is or your enclosure is, the less strong or the weaker the relationship or the fit is. The more it forms a straight line, like we see back up here, if I draw it right around, that's a very straight line. So again, that's more of a better fit or a stronger fit. Same here. Going around those points is a stronger fit than compared to these ones. dr is equal to negative 0.8 or 0.18. So again, I'll draw my axes. So negative means it's going down. The 0.18 means it's very weak or it's a weak relationship. So here we're probably going to see the points spread out a bit more. Right? There's still a little bit of a pattern that we can see. But because the points are more spread out, they're all over the place, they don't really show us too much of a trend. Maybe we'll say that's a good line of best fit there. Again, if we draw a line around our points, we can see it is becoming more box-like. So again, a weaker fit. It is negative because our line of best fit would be going down. So I'd say that's a good representation of that. Lastly, r equals 0. So there is no relationship between the two variables. So this means that generally speaking, the points tend to be all over the place. Now they're not going to form exactly like four corners and things like that, but generally speaking, the points are all over the place. There's no way I can really draw a line of best fit because I don't know if it's increasing or decreasing based off of the values that I have here. And again, if we draw an enclosure around, we can see that we get a very box-like enclosure. So that's a good kind of tip or trick to figure out what your R value might be, or if what you drew makes sense. So we're going to look at a couple of examples now where we are going to create a line of best fit. So in this case, we're going to go back to the graph of the arm span versus the height data, and we're going to draw an approximate line of best fit. We're going to use 2 points on this line and calculate the slope and determine the equation of the line of best fit by hand. So we're going to do that first. So we have some data here. Now this is a little bit different from the data that we collected in our class or from the previous lesson, but it still applies to what we're doing here. So we want to draw our line of best fit, and our line of best fit should go through kind of some key points, or try to go through as many points as possible while still applying or still being related to the trend or still showing the trend. So if I'm going to go through, let's see. Say maybe about there. That looks like it tries to go through as many points as possible. You are going to have points on either side that aren't necessarily on that line. That's okay, right? Again, we're just making an estimate. We're trying to do the best that we can by hand. When we're dealing with this on the computer, it won't be as guessed, right? Or it'll be more accurate on the computer. So we drew our line of best fit. We want to select 2 points on this line. So I'm going to select one down here. I'm going to try to look for ones that are nicely on the grid line. So 140, 130, and let's say here this looks about 190, 189. So those are my 2 points that I'm going to use. Right, so you may have to refer back to grade 10. Right, we want to try to find our slope of the line and then our b value or the y-intercept. So in this case, it might be easier just to create a quick table. X, y, we have 140, 130, 190, 189. So depending on how you learned to find the slope of a straight line, you might look for the change in y and the change in x. So 189 minus 130 gives us 59. And from 190, or from 140 to 190, that's 50. So then my slope, which is equal to the change in y over change in x, is equal to 59 over 50. Which gives me 1.18. So that means my slope is 1.18. What we're going to do now is take this slope plus a point. I'm going to use the 140, 130, the nicer numbers. And I'm going to plug them into our equation. So I'm going to substitute them in to an equation. Y equals mx plus b. Right, the equation of a straight line. We then have y, which is 130, equal to m, which is 1.18, times x, which is 140, plus b. Now we're going to try to solve for b. So 165.2 plus b. This value we're going to move to the other side. When we do that, we end up subtracting. And we get negative 35.2 equals b. Now we have enough information to come up with our equation. Y equals we'll use the color codes. Y equals 1.18 x and then minus 35.2. So this is our equation of the straight line that we came up with. So that's the equation of our line of best fit. Now we can use this line to make predictions if we wanted to. It would be a little bit more accurate than the predictions we made in the previous lesson. So that's the main thing. We want to find the line so that we could make predictions if we wanted to. And when we come up with this line, or sometimes it's called a linear regression using technology, it gives us the R value. So it tells us how closely related to a straight line is this, right? And that's what we're going to do next. So next, we have the overall marks of grade 12 students that were recorded as well as their attendance record. So all the marks are a percentage out of 100. So just a little bit of the background. So we have our students here. Now we want to go through and we want to create a line of best fit. We're going to use Desmos for this. So in order to use Desmos, what we have to do, again, go desmos.com, we go to a graphing calculator. We want to enter a table. I'm not going to list the points one by one, right? So I'm not going to do something like this. I'm going to say 45. I'm not going to do that, even though it will give me the points. So I see that one value here. I'm not going to do this for every single point because this won't allow me to create my linear regression. I want to create a table. So I want to enter in, go plus, table. Now I want to enter my x value and the y value. So again, it depends on what you're looking at. We're going to keep the absences as your x values to determine, okay, if do your absences affect your overall mark. So you'd put in 1, Let's see if we go back. Oh, sorry, it was 2. So the first one would be 2, 82, 1, 34, 5, 66, and so on. And we'll see those points being plotted. You can there's a little, if we enter another one, say 286, you see a little plus or magnifying glass here. If you click on that, it kind of zooms your graph to fit the points that you have. So we have our data here. You go through and you continue to enter this information in. I've already gone through and done that. I'll take this out. I'll take my line out. So I've entered in my data. Right, so we can see all of our points here. The next thing we want to do is now create the equation of a line. So we're going to go over back to our side where we enter in our equations or our tables. We're going to click below and we're going to type in the following. y1, and then we're going to do a little squiggly line, or a mustache you might call it, y1, squiggly line, m, x1 plus b. So by doing that, that tells the software, tells Desmos to create a line of best fit. And we can see the values down here as well as an R value. So for our equation of a line, we would get y equals m, which we're told right here is 1.18, we'll say. Actually, let me use a different color. 1.18 x, and then the b value is right below, so plus 57.7. So that's our equation of our line. That's the accurate equation of our line based off of Desmos, based off the software actually calculating it. So this is our line of best fit. So it's where it goes through as many points as possible and has the points kind of roughly balanced out on either side, as well as close to the line as possible. We do also have the R value. So this software, when we create the line of best fit, it will give us the R value, which in this case is 0.2163. So that R value tells us how well does our line of best fit the data. And we would say that it's a weak fit. It's in that lower portion on our spectrum. So it is a weak fit. It doesn't mean that there is no relationship between the number of absences and the mark. It's just saying that there's a weak one based off of the data we have. Maybe we get more points or more data, we get a little bit more accurate data set, and therefore line and our R value increases. So that's how you create a scatter plot in Desmos and come up with a line of best fit. Now, we are going to refer back to the line of best fit and the R value, but we're not going to really need the graph or the scatter plot anymore. So how well does the regression, or in other words, how well does the line fit the data? We'd say it's a weak fit. And you might say R value is only 0.2163. So by just stating that tells me that it's a weak fit. All you have to do is state that R value, and which will explain that it is a weak fit. If Chester had 4 absences, what would you expect his overall mark to be? So this is where the equation comes into play. So we have y equals m, which is 1.18 x plus 57.7. Now, when we're told one piece of information, in this case 4 absences, we have to understand what that 4 represents. It's going to represent either the x or the y value. So in our case, the X value represented the absences, and Y represented the percent or the mark. So when we're given one piece of information, we can plug that in. Y equals 1.18 times 4 plus 57.7. So if Chester had 4 absences, we would expect him to have a mark of 62.42. So we would expect him to have this mark. Therefore, he would have a mark of 62.42%. So that's the mark that we would expect him to have. And essentially, it's the same thing. We'll go back to our graph. It would be the same thing as saying, okay, 4 absences go over to 4, go up to our line. We can actually see that 4 would be 64.425. We rounded a little bit, but it looks pretty dead on. So it would be the same idea as that we did in the previous lesson, where we just kind of drew a point and saw where it kind of was on the line. By having this exact equation, we can plug the value in, so it would be the same thing as scrolling across and finding, oh, there's 4. That's the mark that we would expect them to have. D, so if I had a mark of 90%, how many absences would you expect me to have? Oops, we'll bring it back. So in this case, it's slightly different because this is telling us a mark of 90. So in our equation, y equals 1.18x plus 57.7. This is now telling me the y value, and I need to solve for x. So in my equation, I'm going to replace 9 with 90 equals 1.18x plus 57.7. I'm going to move this to the other side. When I do that, it becomes the opposite. So 90 minus 57.7 equals 1.18x. You get 32.3 equals 1.18x. And to get it by itself, we divide. In which case we get 27.4 is equal to x. So therefore, with a mark of 90%, you would expect, say, 27 absences. So you can see how that may not actually make sense based on what we know about absences and needing to be at school to do schoolwork and to learn. But based off of the data that we have, that is what we're predicting. Now, if we gathered more data than the few students that we had here, and we may have a better sense. But right now, what this is saying, and we can even see it in the graph, is that the more absences you have, the higher your mark will be. Again, based on what we know that's most likely not true, but based on our data that we've collected, it is. Is there some bias in there? Yes, right? In terms of the number of people we sampled, how we sampled them, it's not the most bias-free. But again, we're not too concerned about that. The main thing is just being able to use the technology to come up with a scatter plot and a line of best fit, or make a line of best fit by hand, and then using that, or being able to use the equation to calculate for missing values. As well, in general, understanding what the R value represents and what the different R values might look like on a graph.